Welcome to the 7th lecture of Open Course on Diffusion in Multi-Component Solids. In this lecture, we will derive the expression for entropy of mixing for an ideal solution. In order to give you a flavor of multi-component thermodynamics, we will apply this treatment to an n-component solution. So, we are going over solution thermodynamics. Last class we evaluated partial molar Gibbs free energy of mixing of constituent atoms or elements based upon assuming the process of forming solution to be equivalent to evaporation of 1 mole of the constituent from the pure element at constant temperature and pressure Pi0, then reducing the pressure of the vapor from Pi0 to Pi, which is the vapor pressure over the solution, and then condensing that 1 mole from the vapor phase into the solution. With this, we got the expression for partial molar Gibbs free energy of mixing of the component I as RT ln AI, where AI is the thermodynamic activity of component I in the solution. And so, we get molar Gibbs free energy of mixing if we form an n component solution as RT sigma ln AI equal to 1 to n. Sorry, there should be a factor xi. So, for a binary solution of A and B, we will get delta Gm to be RT XA ln AA plus XB ln AB. So, now we will go over couple of models of forming the solution of condensed phases. We will talk particularly about solids, so that we understand how the process occurs physically. Okay. So, delta Gm or the molar Gibbs free energy of mixing can also be written as delta Hm minus T delta Sm. This is at constant temperature and pressure, where delta Hm is molar enthalpy of mixing and delta Sm is the molar entropy of mixing. So, the contribution to delta Hm or the change in enthalpy associated with the process of mixing, the contribution to it is mainly from the changes in the types of bonds, right. So, when we form AB solution from pure A and pure B, right, in pure A and pure B there are only AA and BB pairs. When we form the solution, some of the similar atom pairs will be replaced by AB pairs. Now, AA, BB and AB interactions are not same, so it causes changes in the potential energy, which will lead to change in the enthalpy. So, that is the change in enthalpy and change in entropy. Obviously, when you form a solution from pure elements, in the solution there are more special configurations available, and so there is a change in entropy. So, we will first look at the ideal solution model. In an ideal solution, essentially the enthalpy of mixing is 0, which means there exists no interactions between the atoms, or if there are interactions they are all same. So, it does not matter what pair we are looking at, AA, BB or AB, the interactions are all same. Okay. And the entropy of mixing is essentially all from the change in configurational entropy. Okay. So, let us try to evaluate delta S configuration for the process of mixing. So, suppose we form an n component solution by mixing n1 atoms of element 1, n2 atoms of element 2 and so on, right. So, we have n1 atoms of 1, n2 atoms of 2 and so on, and n atoms of n. So, the total number of atoms will be the summation of all the atoms right. So, before mixing, let us call the entropy of the system before mixing, and we are talking here about only the configurational entropy. What should be the entropy of the system before mixing? 0, right. So, how many configurations are available, right? We know all 1 atoms are on lattice of 1, all 2 atoms are on lattice of 2 and so on, right, and all 1 atoms are identical, all 2 atoms are identical, all 3 atoms are identical. So, there is only one possible way in which these atoms can be arranged before mixing. So, by Boltzmann equation we know S1 is k ln omega, omega is the number of configurations possible and omega here is 1. So, S1 is 0. So, delta S configuration is essentially S2 minus S1, which is equal to S2, where S2 is the configurational entropy after mixing. So, let us try to evaluate S2. For that we need to evaluate the number of possible configuration after mixing, right. So, let us, this is omega 1, let us call this omega 2. So, how do we evaluate that? To form a solution, more particularly we here talk about random solution, which means there is a random mixing. Okay. So, all n1 atoms are distributed randomly on the available n sides, n2 atoms are distributed randomly and so on. So, in that case, how many number of different ways we can arrange n1 atoms on n sides? That will be NC n1. Now, once we arrange n1 atoms, there are only n minus n1 sides are left. So, we select n2 atoms and arrange them on the available n minus n2 sides. So, there are n minus n1 C n2 number of ways possible in which n2 atoms can be arranged. After we arrange n1 and n2, number of sides left are n minus n1 minus n2 and n3 atoms can be arranged on these many sides in n minus n1 minus n2 C n3 number of ways, right, and so on. So, let us write the formula for NC n1 should be n factorial divided by n1 factorial times n minus n1 factorial times n minus n1 factorial divided by n2 factorial times n minus n1 minus n2 factorial times n minus n1 minus n2 factorial divided by n3 factorial times n minus n1 minus n2 minus n3 factorial and so on. So, we can simplify this cross terms will just keep getting cancelled, and so finally, we have the expression for omega 2 as n factorial divided by n1 factorial, n2 factorial, so on till n factorial. So, we can write S2 is equal to k ln omega 2 is nothing but n factorial divided by n1 factorial, n2 factorial, so on till n factorial. So, how do we simplify this further? So, each number here is typically a very large number, right. Even if when we talk about 1 mole of solution, that n is going to be 6.023 times 10 to power 23 number of atoms, right. So, if we are dealing with large numbers, we can use Stirling's approximation. It says ln x factorial is equal to x ln x minus x for large values of x. So, if we use this approximation, we can write S2 is equal to k ln, we can rearrange this ln n factorial minus ln n1 factorial minus ln n2 factorial and so on, and we can use Stirling's approximation for each of the ln term. So, this becomes k times n ln n minus n minus n1 ln n1 plus n1 minus n2 ln n2 plus n2 and so on. So, now we can see this terms n1 plus n2 plus n3 till n, they add up to number n, and so this will get cancelled, and n again can be written as n1 plus n2 plus n3 till n. So, we can again do the rearrangement, and we get S2 is equal to k n1 ln n over n1 plus n2 ln n over n2 and so on. Now, if we take the inverse, we can take the negative sign out. So, this will be essentially minus ln n1 by n, and n1 by n is the atom fraction of 1 or mole fraction of 1, which we call as x1. So, we can write this as S2 is equal to minus k n1 ln x1 plus n2 ln x2 so on till xn ln nn ln xn. So, if we multiply and divide by the Avogadro's number, so if we multiply k by Avogadro's number, k times Na is what? Gas constant R. And we have to divide inside by Avogadro's number, N1 by Avogadro's number. Number of atoms divided by Avogadro's number is number of moles. So, this will be N1 ln x1 plus N2 ln x2 so on till Nn ln xn. Right. So, basically delta S configurational in this case should be equal to S2. This should be more appropriately delta S prime, because we are talking about the entire system. If we say per mole, we have to divide by the total number of moles. So, we can get rid of this prime sign. So, the molar configurational entropy of mixing, we divide this by total number of moles. So, N1 by total number of moles will be again the mole fraction of 1, N2 divided by total number of moles will be mole fraction of 2, and so on. So, we get the expression for configurational entropy change to be minus R x1 ln x1 plus x2 ln x2 till n. So, basically delta S mixing for ideal solution, which is all because of the change in configurational entropy, should be equal to minus R sigma xi ln xi, I is equal to 1 to n. Obviously, since delta Hm is 0, so delta Gm ideal should be equal to minus T delta Sm ideal, and so delta Gm ideal should be equal to RT sigma xi ln xi, I equal to 1 to n. So, this is the expression we got for the Gibbs free energy of mixing for an ideal solution. If you remember, we also derived an expression for Gibbs free energy of mixing for ideal gases, and they come out to be same, right. So, if we plot this as a function of composition, so let us do this for just a binary solution of say components A and B. So, for binary ideal solution of A and B, we can write delta S m I d is equal to minus R x A ln x A plus x B ln x B, and delta Gm I d will be R t times x A ln x A plus x B ln x B. So, let us plot both these quantities as a function of composition, say x b. So, x a and x b are fractions, right. So, these logarithmic terms are negative, which means delta Sm I d has to be positive, and the way it varies with composition, you can plot it, will be like this. So, this is delta Sm I d, and delta Gm I d you just need to multiply by minus T. Since this is positive, delta Gm I d will be negative, but you need to multiply by a factor of T. So, this is delta Gm I d. So, how do we interpret this curve? obviously you see a minimum somewhere. So, do not interpret it as the composition corresponding to this minimum is the most stable solution. Okay. So, the way it has to be interpreted is at a given composition. So, let us say we are considering this composition, let us say XA1 XB1. What does this mean is delta G mixing for ideal solution of A and B of composition XA1 XB1 is negative, which means if we mix A and B in these proportions, there will be a negative change in Gibbs free energy, which means that mixing process is an irreversible process. Okay. So, that is the way it has to be interpreted. So, this was for ideal solution. We will now look into the non-ideal solutions, that will be in the next class.